What if the edge of the universe isn't a physical wall, but a boundary made of time itself? Imagine a horizon so vast it contains trillions of galaxies, yet beyond it, the universe continues, forever hidden from our sight. In this episode, we're exploring the ultimate frontier, the observable universe, and the profound limits light imposes on our understanding. The observable universe is therefore not the edge of existence, but the edge of communication. For astronomers, it is a sphere encircling everything we can ever observe, the observable universe. Beyond this frontier lies not a wall, but darkness unlit by any message that has yet reached us. The limit is not imposed by space, but by time. Light travels at a finite speed, 299,792 kilometers per second. That constancy, which defines the structure of reality, also defines how far we can look. Because the universe has existed for 13.8 billion years, one might imagine the farthest visible distance to be 13.8 billion light-years. But space itself has expanded during that time, stretching the intervening distance. The galaxies whose light began its voyage shortly after the Big Bang are now nearly 46 billion light-years away. Every telescope gazes backward through time. The sun we see shone 8 minutes ago. Andromeda's light began its journey 2.5 million years ago, when early humans first learned to strike sparks against stone. The most distant galaxies ever observed by the James Webb Space Telescope emitted their light over 13.4 billion years ago. When that light left, the universe was only 350 million years old, a newborn cosmos barely emerging from cosmic dawn. We are not observing them as they are, but as they were nearly to the beginning of time. The farther we gaze, the younger the universe becomes. Between those distant galaxies and us lies a veil, the cosmic microwave background, CMB, the oldest light we can ever see. Emitted about 380,000 years after the Big Bang, it comes from the moment when the universe cooled enough for electrons and nuclei to combine into neutral atoms, allowing photons to travel freely. Before that, the universe was opaque, a glowing fog that scattered light endlessly. The CMB is the echo of that turning point. Radiation stretched into microwaves by 13.8 billion years of expansion, faint yet still observable as a uniform glow filling all directions. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, this background proves that the universe once existed in a hot, dense state. Tiny variations in its temperature, differences of only 1/10,000th of a degree, mark where density fluctuations seeded galaxies and clusters. Space probes such as COBE, WMAP, and Planck mapped those variations with increasing accuracy, transforming the CMB into a cosmic baby picture, a snapshot of the universe's childhood. If you're captivated by these glimpses into the universe's past and future, consider hitting that subscribe button and joining us for more explorations into the cosmos's deepest secrets. As cosmic expansion continues, the light from distant galaxies stretches. Its wavelengths lengthen, shifting toward the red end of the spectrum. This phenomenon is called cosmological redshift. Redshift is both a measure of distance and of time. A galaxy with a redshift, Z, of 1 is seen as it was 7.8 billion years ago. One with Z equals 10 dates back to roughly 480 million years after the Big Bang. Astronomers use these measures to construct a look-back timeline, a scale where distance and history merge into one continuum. Beyond Z, at approximately 1,100 lies the origin of the CMB itself, light so stretched that its wavelength has grown from visible orange to millimeters. To look farther back than that is impossible with photons. The universe simply wasn't transparent before that epoch. For earlier epochs, the first seconds, the first microseconds, We rely not on light, but on mathematics and high-energy physics. There, matter dissolved into quarks and gluons, and time as we know it may have begun. When Edwin Hubble announced in 1929 that distant galaxies were receding faster the farther away they were, he demonstrated that space itself expands. Galaxies are not exploding apart into pre-existing emptiness. The fabric between them stretches. This expansion carries galaxies beyond each other's reach, not through motion, but through geometry. The farther a galaxy is, the faster it recedes, until at the cosmic horizon, its apparent velocity equals the speed of light. It is a universe vast, accelerating, and filled mostly with the invisible. What mysterious energy is shaping the ultimate destiny of everything we know, potentially leaving our future night sky empty and isolated? In 1998, observations of distant supernovae revealed something even stranger. The expansion is accelerating. The cause was attributed to a mysterious dark energy, an unseen pressure making space stretch faster over time. If this acceleration continues, distant galaxies will eventually move away so rapidly that their light can no longer reach us. Over tens of billions of years, the night sky will grow emptier. Galaxies now visible will fade beyond the cosmic event horizon, leaving only the local cluster tethered by gravity. This fate, an expanding isolation, is one possible destiny of the cosmos. Others have been proposed: a big crunch, in which gravity halts expansion and reverses it; a big rip, where acceleration grows so extreme that even atoms are torn apart. We often picture the edge of the observable universe as a physical surface, yet it is not a boundary like a wall, but a limit imposed by time. Beyond 46 billion light-years, light simply hasn't had enough duration to reach us. That horizon expands slowly as centuries pass. Each new year, more photons arrive from slightly farther away. The observable universe grows not because space shrinks, but because more of it comes into view. Still, there is a deeper limit: the event horizon, defined by future visibility. Even if we wait forever, there are regions we will never see, because space between us and those regions expands faster than light can cross. For all practical purposes, they are beyond connection, forever causally separate. In cosmology, distance becomes relative, and the notion of beyond acquires temporal as much as spatial meaning. Modern cosmology suggests that the observable universe is only a small patch of a much grander whole. Moments after the Big Bang, the universe underwent an episode of inflation, an exponential surge in scale that stretched quantum fluctuations across unimaginable distances. Inflation explains why the cosmic background looks so uniform and why space appears geometrically flat. Any curvature was smoothed like wrinkles pulled tight on a balloon. If inflation occurred, the universe might be vastly larger than our observable portion, perhaps infinite. Different regions could lie forever beyond contact, like separate islands expanding faster than signals can travel. Some theories even propose that inflation may create multiple bubble universes, each with its own physical constants, a speculative landscape called the multiverse. Whether such realms exist or can ever be tested remains uncertain. Yet they flow naturally from the mathematics describing cosmic beginnings. Is the universe finite or infinite? Observations by the Planck satellite indicate that large-scale geometry is remarkably flat to within 0.4% precision. If it curves at all, the radius of curvature exceeds 250 times the observable horizon, effectively immeasurable. Flatness means that parallel lines never meet, and that space continues evenly in all directions. Thus, the universe could extend forever, or loop back on itself at scales too enormous to detect. Either way, the part we can see is a finite window onto a possibly boundless whole. Within that window, Matter arranges in the cosmic web we traced earlier, filaments of galaxies, clusters and voids, but beyond it the pattern may or may not persist. In the absence of light, our equations must take the place of vision. What does edge mean to beings who can think but never cross it? It is a horizon of knowledge as much as of light. Everything beyond our view lies hidden not by distance alone, but by physics itself. No telescope, however powerful, can capture signals older than transparency or faster than expansion. The universe guards its infancy and its outer reaches behind the same veil. And yet, this veil defines wonder. Because there is a limit, curiosity persists. The edge of the observable universe becomes the mirror of human imagination, a line we strive to approach, though we know we cannot pass. Astronomy, in that sense, is the art of reading light's silences as carefully as its speech. To chart the universe is to capture it before its signals fade. Over the next trillions of years, stars will exhaust their hydrogen, galaxies will fade, and space will grow darker. When the cosmological horizon surpasses every distant light source, each surviving observer will inhabit an increasingly black sky. The cosmic microwave background will redshift into radio waves thousands of kilometers long. Atoms will decay. Black holes will evaporate slowly through Hawking radiation. Eventually, only thin dusts of elementary particles will remain, diffused into near-zero temperature. This distant epoch, often called the heat death, marks the universe's final equilibrium, where energy is so uniformly distributed that nothing more can happen. Between now and then lies the age of consciousness and discovery, our brief window when light still carries evidence of origin. In this sense, each act of observation becomes an act of preservation. We can describe equations, imagine continuations, but those speculations remain unseen. To measure such distances is a triumph of perception. To understand them emotionally is nearly impossible. But perhaps magnitude is not scale, it is context. If the cosmos were smaller, we might not ask questions. If it were infinite, we would not need to measure. Its immensity gives rise to perspective, and perspective births thought. Within every photon from the edge of the observable universe lies a story 13.8 billion years in transit, a message about temperature, composition, and movement. Together they form a cosmic autobiography written in light. We read it, one wavelength at a time, constructing from that faint data the tale of everything. And beyond the horizon, what then? Light defines reality's boundary. Each observer is the center of their own sacred sphere, 46 billion light-years in radius. Every conscious being anywhere in the universe occupies a similar bubble of sight. Together, these overlapping spheres ensure that every point is both center and edge, a symmetry that honors no location above another. When we look toward that horizon with telescopes and mathematics, we do what the first humans did when they looked over an ocean at sunset. We wonder what lies beyond. The answer, still traveling toward us, is written in light older than memory. We need only wait and listen to the universe arrive. If you've been awestruck by the ultimate frontier of the observable universe, make sure to subscribe for more incredible journeys through the cosmos. And to continue your exploration of the universe's wonders, click on the video appearing on your screen right now.